from Brendan. I'd just like to say I'm a huge fan of your work. You're my biggest hero. I've always been interested in how reality works. I followed physics, learning concepts of how our reality works, looking for an answer as to where reality itself came from and if there's a purpose to all this. I've never been religious and I've followed the mainstream materialist view in physics for a while. I was too a materialist and saw everything as the materialist physicists did. As you know, they're very good at answering how everything works, but they're very bad at answering fundamental questions like why everything is the way it is and where it truly came from. I started losing interest slowly in their description of reality, where it came from, that is, because something deep in me said it wasn't quite right. Looking at the anthropic principle, I realized the universe was too perfect to have come into existence like this on its own. Something deep in me told me that something else was going on that these physicists were missing. I then began looking into spirituality for answers, but their answers were somewhat unsatisfactory as well. I like to think I have a physicist mind. I look at everything with passion, to knowing how it works down to its most fundamental level. I've always been like this. To make a long story short, I saw a comment on a video from a spiritualist teacher. Someone mentioned your work and that you're a physicist. I jumped in joy because at this point I thought I had to avoid physics altogether to find the answer of existence. I immediately looked up your work and never stopped learning your content since. Your explanation on the double slit experiment is my favorite. I studied that experiment for a long time trying to understand it. When I heard your explanation on it, I shed a tear of amazement and gratitude. It makes complete sense. You are my hero. You provided me the answer I've been looking for my whole life with logical scientific understanding. In my eyes, you're the biggest celebrity in the world. To do what you've done to answer humanity's biggest, most important question is a very big deal. Thank you, Tom. Thank you so much for dedicating your life to modeling the reality that created our universe. That is the biggest deal to all human accomplishments and goals. I will be supporting you in your work every day as much as I can. I would love to join your fireside chats, your VIP club, and everything else that can be joined. My greatest desire in life is to meet you in person. I will forever remember that moment till the day I die. I want to get my degree in physics and hopefully help to be one of the physicists helping you explain to the world how it works. Physics is my greatest interest and it'd be an honor to be able to help you convince the world how our reality actually works. So thank you again, Tom. I can't thank you enough. I look forward to seeing more of your material as I do this every day. And that's from Brendan.
Well, that was nice, but I didn't hear a question in there.
There isn't a question. There isn't a question, but I think it would be appropriate for you to comment on the physics experiments that are going on now as we speak and how that will contribute to what Brendan finds so exciting.
Yeah. Okay. Well, thank you, Brendan. That was very lovely. I appreciate that feedback. It's always feels good to know that a plan is actually working, that people are listening and understanding. You've no doubt heard my explanation of why all those universal constants, why they're like that, that it's the evolutionary process of the simulation that is simulating this virtual reality. But I do have some other experiments going on that also tie into physics and into science. It's a set of experiments that I presented at a talk in Los Angeles in 2016, and you can look at those if you go to my YouTube and search for MBT-LA 2016. That's the title of it. And you will find there 2 days worth of talk. And the first day is basically talking about virtual reality model. In the morning, I explain virtual reality. And you might find it interesting because I point out a lot of like the footprint, if you will, of virtual reality. You know, we see something in, you know, people ask, say, how can you tell we're in a virtual reality? Well, virtual reality leaves its own footprints, you know, it leaves its own markers. And if you are aware of what those markers are, then you can see that indeed this is a virtual reality because the markers of a virtual reality are there. And I think I point out maybe 6, 7, 8, 10, 12 of these virtual reality markers, which you might find interesting in the early part. And then in that afternoon, I describe a set of quantum mechanics experiments that I dreamed up that will do two things. One, they will lend a lot of strong evidence to the idea that our reality is indeed a virtual reality. And secondly, they will also lend a lot of evidence to the fact that consciousness is the computer. The experiment, if they work as I expect, will do some things that are impossible. You know, just like the double slit does something that's impossible. It sends one particle at a time toward two slits, and those particles don't just pile up behind each slit. Those particles, for some unknown reason, distribute themselves in an interference pattern. And you hear physicists saying things like, well, the particle goes through both slits at the same time, which is obviously silly. Or, you know, even the probability goes through both slits and interferes with itself. Things like that. Like you hear people also saying the cat, Schrodinger's cat's both dead and alive. You know, it's in a superposition of two states. And all of that is kind of nonsense. There is no cat that's both dead and alive. You know, it doesn't work like that. It's a simple matter of when one takes a measurement, the system makes a random draw from a probability distribution of all the possibilities, and that's what happens in that instant. You see? So in that, with that Schrodinger's cat, you're going to make a measurement. Let's see whether the cat's dead or alive. Well, at that point, you take a random draw from a probability distribution of all the possibilities, which has to do like how long's that cat been in that box with that radioactive source and that Geiger counter. So you do look at those probabilities, then you take a random draw from the probability distribution, and then the system renders that answer, renders the cat either being dead or alive. So it's a matter of, what do they say? The physicists say, collapsing the wave function to a physical result. Well, that's the big mystery in physics. You know, what is this collapsing the wave function? How does that work? What do you mean that somehow you have a probabilistic wave function and it collapses to a physical result? You know, that's kind of the thing. You've seen the joke on the board where they have all this math and then there's ... and then a miracle occurs, you know, and then the answer is written down over on the other side. A result is the result of the collapse of the wave function. That's one of those, then a miracle occurs and we get a physical particle. Physicists don't really understand that at all. And that's because they misinterpret the mathematics. Their mathematics is indeed about probability distributions, but they see that there are possibilities, and they then come to the conclusion, because this is a material world in their reality, in their minds, they see it as a material world, then they see this, you know, this cat is a material thing in a box, and there's two of them, one's dead and one's alive, and when you open the door, one of them will manifest. Well, that's not it at all. One of them is rendered, is what the answer is. One of them is rendered. And anyway, so I've done these experiments to do some magic, just like double slit. And one of the magic things is that the researcher doing the experiment will be able to predict how a nucleus, a radioactive nucleus, decays. And by that I mean when a particle gets thrown out of a radioactive nucleus, that's what radioactive decay is. Particles get tossed out. They get tossed out in a random direction. They get tossed out in, you know, any direction. And in this experiment, I'll have a detector, two detectors, one hemisphere and another hemisphere with a radioactive particle in the middle. So it'll either come out in hemisphere A or it'll come out through hemisphere B. And there's a 50-50 chance, if you just guess at it, that you'll be right because it's random. But in my experiment, you'll be able to predict it. Next particle is going to come out through A. And sure enough, it will. Next one's going to come out through, A again. And next one is going to come out through B. So the experimental will be able to predict how that random event isn't random, how that random event can be predicted. You see, well, that's patently impossible. The other experiment that does something that's impossible is a similar thing, and it's a similar process, and it will predict what a photon will do when it gets to a beam splitter. Again, a beam splitter will have a 50-50 chance that the particle will either be reflected or transmitted through this beam splitter. So it gets to this device, and it'll either hit this device and bounce this way, be reflected, or it'll go right through that device and be transmitted. And again, this is a random, natural, random function. And the experimenter will say, the next photon is going to be transmitted, and the next one is going to be reflected, and they will be able to tell what's going to happen when that photon gets there in advance. Okay, so if they work that way, that will be interesting, and it'll give us two more experiments that provide minor miracles that do things that shouldn't be able to be done, like particles all just for some reason rearranging themselves, in a interference pattern. Well, of course, that's because when they take that random draw from the probability distribution, that probability distribution looks like an interference pattern. That's what the probability distribution looks like, you see. So you take enough random draws from it, eventually you reproduce the pattern. That's what that means. So in any case, and why would the system have a interference pattern? Because that way there is no conflict between optics and quantum mechanics. The boundary between those two now matches perfectly. Otherwise, there'd be this glaring conflict in our reality where those two didn't go together. So the system had to give it that probability distribution so that that conflict doesn't exist, because a good virtual reality is one that you can't tell that it's a virtual reality. So anyway, I've got these experiments, and another one that's of interest is basically to explore a little bit about what they call the observer paradox. Why is an observer important? Why, they call it sometimes the measurement problem rather than the observer paradox. It's the main thing. It basically says when you observe which particle or which slit the particle goes through, then suddenly you no longer have coherence. You don't get an interference pattern. You just get a pile of particles behind each slit. Well, that's because the measurement, when you make the measurement, the system has to create something there in the physical world. When you have that thing, that's the wave function collapsed to a physical particle. Once you have a physical particle, it can't do anything other than act like a physical particle, which is travel in a straight line and land on the screen right behind the slit. When you don't make that measurement, it's just a probability distribution. It's not constrained. So then the random draw gives you something else, you see. So at the slit, the random draw is out of a distribution as well. There's a probability that it'll go through one slit or the other. And it's usually a 50-50 probability. And you take that random draw and, it just went through slit A or slit B. You see, that's the distribution there. So anyway, the science continues. The update on that is that I'm expecting any month now, that we're going to get results on the very first experiment, which is one to basically resolve an argument between me and standard quantum theory, which has modified quantum physics away from what used to be called the Copenhagen interpretation. Okay, Copenhagen interpretation really wasn't an interpretation. It was just how those scientists explained the results that they got. It really wasn't that they were interpreting something. They were saying, here are our results. This is what happened. And because it violated materialism, physicists didn't really like it. They wanted to do something else. And eventually they did do something else. And now physics is kind of tossed out that Copenhagen idea, and they have their own more materialistic idea. And I disagree with that, because my theory of everything, my big toe, does a derivation of quantum physics from first principles, and it basically supports Copenhagen. It supports what the Copenhagen folks said. Now, there were a lot of smart guys there at Copenhagen. You know, they were probably the best of the best that we've seen in a couple of centuries as far as physics goes. So my theory supports their results. It says they should get those results. So current physics says, no, it doesn't really work like that. So we'll see in that first experiment. So that's what's going on. So there's more to come. And I'm glad you have been enjoying MBT and that you found a lot in it and it's giving you the answers you like, but the answers are still coming in. So stay tuned.
Yes.
And we'll see. Now I have another experiment also working on this. It's the first experiment, but I'm doing a second place now. And so I have two different groups of scientists doing this first experiment. And the reason I've done that is because, one, nobody believes just one experiment done once. You know, it's not really good science until several people do it several different places. So I just start that process in parallel. And secondly, because if I can demonstrate that today's physics is wrong, they should go back to Copenhagen, then hopefully that will get me enough attention. That will make doing the other experiments easier, because I'll have more people looking, more people interested, and trying to get those funded will become a lot simpler. So anyway, that's what's going on now. So thank you for the nice words. I really do appreciate it.
Thank you, Tom. And thank you, Brendan, for your support of Tom's work. Thanks, Tom.